all, today we will be discussing about how Newton's rings are formed. We have already discussed about different types of interference fringes. We already discussed that interference fringes are produced by two methods, division of wavefront and division of amplitude. And Young's double slit experiment uses the division of wavefront method, and the division of amplitude means reference by partial reflection and refraction by using a lens or mirror. So fringes are of two types. Interference fringes obtained using division of amplitude are of two types: fringes of equal inclination and fringes of equal thickness. And fringes of equal inclination is known as Heidinger fringe, and fringe of equal thickness is known as Fizeau fringe. And Newton's ring is an example for Fizeau fringe. And we can study. Let us study more about how do this Newton's ring is produced and how the experimental arrangement is used to measure or determine the wavelength of light and the refractive index of a liquid. Two types of fringes of constant inclination and fringes of constant optical thickness. So the corresponding to one value of angle of refraction, there will be either a bright fringe or a dark fringe, and such fringes were first investigated by Heidinger, and so they are known as, such types of fringes are known as Heidinger fringes, and they are fringes of constant inclination. The fringes obtained thus were circular in nature, and the circular interference fringe obtained with Michelson interferometer belongs to these types of fringes of constant inclination. Another type of fringe is fringe of constant optical thickness. Whenever the thickness of the film is rapidly varying, the inclination, angle of refraction r, and the wavelength remains practically constant, and then the path difference depends on the optical thickness of the film. So each fringe will be the locus of all the points of the same thickness. Each fringe will be the locus of all the points with the same thickness. This type of fringes were first investigated by Fizeau, and Newton's rings are an example for this type of fringes of constant inclination. Actually, Fizeau fringes obtained from an air wedge is also a good example for fringe of constant optical thickness. Let us study more about this fringes of equal optical thickness. We have already said that Newton's ring and air wedge are best examples for fringes of equal thickness. So how does this Newton's ring is produced? Newton's rings are produced due to the interference of light by division of amplitude. That means interference produced by the superposition of two similar waves derived from a single wave, either by partial reflection or by partial refraction. So divided parts of the same light travel different paths and are produced to interfere each other. This type of experimental arrangement needs a broad light source, and effects are more prominent and are of great intensity. So we have already said that Newton's rings are produced due to the interference due to partial reflection and refraction, and there will be a plain glass plate, and over which there will be a convex lens. Base is just in contact with the glass plate, and the interference is produced due to the rays reflected from the upper and lower surface of the upper and lower surface of the from here it will be reflected. Say AB be the incident ray, and from B it will be reflected through the same path, and after reaching this lower surface it will be again partially reflected and will travel the same path, and the interference produced due to the interference between rays reflected from upper and lower surfaces of the air film that is formed between this convex lens and a plain glass plate. Actually, this type of arrangement is first suggested by Hooks in 1665, and this is actually investigated by Newton. So it is called the Newton's ring. So let us discuss more about the experimental arrangement. So when this type when monochromatic light is falling on this type of arrangement, we could get a series of concentric bright and dark rings as and reference pattern. So a plano convex lens of large focal length is placed on a plain glass plate. A plano convex lens of large focal length is placed on a plain glass plate, and a thin film of air is enclosed between this lens and the glass plate. We can see that thickness of the air film at the center or at the point of contact between these two substances, or this lens and the glass plate, the thickness of the air film will be zero, and it gradually increases from the center to the outwards. Thickness of the air film will be increasing from the point of contact to the outward. So here a system of concentric circular fringes are produced with the center of the ring system as the point of contact between the glass plate and the lens. This type of circular rings are known as Newton's ring. A system of concentric circular fringes, dark and bright rings can be seen, and this type of ring is known as Newton ring. Alternate dark and bright arrangement can be seen for a monochromatic light source. Colored fringes can be observed if we are using a white light. So let us move towards the theory of this Newton ring arrangement. We have already said that. If we are considering a plain glass plate and over which a lens is placed, a plano large for plano convex lens with a large focal length is placed. A ray AB is incident perpendicularly on this lens. A is incident perpendicularly on this lens, and from the upper surface of the air film it will be reflected along this path. We can say this ABC, and from there it will reach the surface of the plain glass plate, and from there it will be again reflected through the path DCBA. So at D, the ray get partially reflected along this DBA, and two reflected rays will interfere each other to produce dark and bright fringes, depending upon the path difference between two waves. Let T be the thickness of the air film. Let T be the thickness of the air film at this point, or at the point D, and path difference delta between the rays reflected from D and C is equal to 2nt cos r. The path difference of the rays reflected from the point D and C is equal to 2 nd cos r, where n is the refractive index and r is the angle of refraction at the point D. So reflection at the point D is at a denser medium, because it is a plain glass plate, and plain glass plate is having refractive index more than that of a air column. So reflection from the point D is happening in a denser medium. So one of these two interfering beams will suffer a phase change of pi, which corresponds to a path difference of lambda by 2. So effective path difference can be written as 2 nd cos r 2 nd cos r plus lambda by 2. 2 nd cos r plus lambda by 2. So according to the brightness condition in reflected system, path difference is equal to path difference is equal to 2m lambda by 2, or we can say that here t and 2 nd cos r is equal to 2m minus 1 lambda by 2. Path difference for the brightness and darkness condition is, this is brightness condition for brightness, for the fringe to be to appear bright, and the darkness condition is path difference equal to 2m plus 1 lambda by 2. That means here 2nt cos r is equal to 2m lambda by 2 is equal to m lambda. As the air column is having refractive index equal to 1, and the ray is incident, as the ray is incident normally, angle of refraction can be considered as 0, then at D, the point will be bright or dark according to the condition 2t is equal to 2m minus 1 lambda by 2, and this is the bright, for the fringe to appear bright, and for the fringe to appear dark, the condition is 2t is equal to m lambda. So at the point D, the fringes will be bright or dark according to these conditions. So air film has same thickness at all points. Air film has same thickness at all points along the circumference of a circle. We can see the experimental arrangement here. We can see that the air column is having the same thickness. The air film is having the same thickness at all points along the circumference of a circle with the center O and the radius OD. We can see that when we uh, draw a circle here, the radius will be the O and this particular point. So bright and dark ring formed according as the point D is bright or dark. So thickness of air film increases as this D is moving outwards from the point, the center O. So alternate dark and bright rings concentric with the center with the point O will be formed. Here we have to note that the center of the ring system always will appear always dark. Why is that? Like at at the center at the point O, the thickness of air column is equal to 0, and the path difference delta will become lambda by 2. That means that means this is the condition for darkness. 20 cos r is equal to lambda by 2, and this is the condition for darkness. Next we have to derive an expression for radius of m the ring. Radius of m the ring. And also an expression for wavelength of light in Newton's ring arrangement. For this, we are considering again this glass plate and this convex lens, and we are considering the convex lens, the uh, point of contact as O. Let this convex lens radius of curvature is r, and center of curvature of the lens is at the C. You can complete the figure of that lens by extending this to a circle. The center of curvature is C, and the radius of curvature is r. So when we are considering a beam of light, a ray is incident and it falls on the point C. Say a ray of light A B is incident, and it falls here and it is reflected back, and from that point we can call it as D, because C is already mentioned as center of curvature, and this point we can call it as E. So from E, or from the lower surface of the air column, it is reflected, and EDBA and DBA are interfering each other. EDBA and DBA rays are interfering each other. And T is the thickness, and small r is the radius of ring, or radius of a particular circle which is passing through the point E. If we are considering a Newton's ring here, this is the center. O is the center of that ring, and OE is the radius of the ring. And this will be the radius of curvature of the convex lens. So we can write this like DE is actually the thickness of the air column at that point E, and OE is the radius of ring, which is equal to R. So consider the right angle triangle, which is we are drawing a parallel line uh, DF, and we are considering this triangle. Here it cuts at H. So consider the right angle triangle CHD. Here we can see that CD square is equal to DH square plus CH square, and DH is we are drawing a parallel to the glass plate. So this DH is actually similar to this EO. This is equal to, next page, CD square is equal to DH square plus CH square, and DH is nothing but EO square plus CH is, we can see here, CH is CO minus OH. CO minus OH. CH is CO minus OH. So here in this equation, CO minus OH the whole square. This is equal to, here the CD is nothing but the radius of curvature. The CD is the radius of curvature of the lens. So we can write it as R square, and EO is the radius of the ring, the same as OE. OE is radius of the ring. So EO can be written as R plus CO means CO is radius of curvature of the lens. So here it is R, capital R, minus OH is the same as DE. That means the thickness of the air film at that particular point. Therefore R minus T square. This is equal to R square plus capital R square minus 2RT plus T square is equal to R square. Capital R square is in both sides, so we are going to write small r square as 2RT minus T square. Compared to the radius of curvature, the thickness of the air column is very less. So this equation we can simply write like this: R square is equal to 2RT, because a small quantity square is nothing to go, nothing going to do with this large quantity of 2RT. So R square, this minus T square can be neglected, and we can write this R squared as 2RT. Therefore we are getting a new expression which is known as 2T is equal to R square by R. So the radius of the, if Rm is the radius of the mth ring, we can convert this equation as Rm square by R, radius of the mth ring. For the condition for darkness, we know 2T is equal to m lambda. This implies that Rm square by capital R is equal to m lambda. Therefore, we can write this Rm square is equal to mr lambda. This is actually the expression for radius of the mth ring. If Rm plus k is the radius of the m plus kth ring, we can write this equation as Rm plus k square is equal to m plus k into r lambda, where k is just an integer. Next, we have to know what should we do to find out the wavelength of the light used. We have to consider the or calculate the wavelength of monochromatic light used. We have to do this particular step. Rm plus k square minus Rm square is equal to, what is Rm plus k square? M plus k into r lambda minus, what is Rm square? M r lambda. This is equal to k r lambda. Therefore, lambda is equal to Rm plus k square minus Rm square by kr. If dm plus k and dm are the diameters of mth and m plus kth ring, dm, if we are considering the diameter, dm and dm plus k are the diameters of these rings, we know Rm is dm by 2 and dm uh, and Rm plus k is Rm plus k is dm plus k by 2. Therefore, how this equation is going to convert? Lambda is equal to Rm plus k square means dm by 2. Therefore, dm plus k square by 4 minus Rm means dm by 2. Here also Rm can be written as dm square divided by 4. Therefore, the equation becomes 4 common, and this becomes 4 into k r. So this will be the expression for lambda or wavelength of light used. Here we have considered the condition for darkness. If we are taking the condition for brightness, we will get the same result. If we are taking 2t is equal to 2m minus 1 lambda by 2, and by putting this Rm square by r as 2m minus 1 lambda by 2, we get the same equation like this, Rm square and Rm plus k square. And r square m plus k square minus Rm square is equal to k r lambda, and lambda is having the same expression. You can do it by yourself. So by using a simple arrangement of this Newton's ring, we could calculate or we could determine the wavelength of the particular light used by measuring the diameters of the rings, by measuring the diameters of the rings and the radius of curvature of the lens. Now let's discuss about the experiment to determine the wavelength of monochromatic light used. So experimental arrangement is like this. This is experimental arrangement. A monochromatic light, say sodium lamp, is allowed to fall on this plane convex lens using a glass plate, and which is inclined at an angle 45 degree to the horizontal, And this glass plate is used to make the rays fall perpendicularly to the convex lens. So by reflecting from the glass plate, the rays will fall perpendicularly to this plane convex lens. And the rays falling on the convex lens will travel through this lens and through the air column between this lens and plane glass plate, and the rays reflected from the upper and lower surfaces of the air column with air film which is in between this lens and glass plate will interfere each other and will produce interference pattern, and the interference pattern can be viewed through this traveling microscope. And the observation is like this: we could see concentric dark and bright fringes through the microscope. A system of dark and bright fringe concentric circular rings can be observed through this microscope. So, starting from this right hand side, the readings has to be noted. So, we have to move this microscope towards the right hand side and focus the crosshair onto the 18th or 20th ring tangentially, and taking note the readings of that ring, and then focus that crossword to the 16th ring, and then to 14th ring, and then to 12th ring, and so on, and up to second ring. Up to the second ring, readings has to be noted. Then we have to move this crossware or move this microscope towards the left hand side and take the readings of second ring, and then fourth ring, and then sixth ring, and then etc up to the 18th ring. So we could get the diameter of a particular ring by taking the difference between the readings on the left and right of each ring. For example, if we have to calculate the diameter of this particular second ring, we could take the difference between this reading noted for the second ring in the right and the second ring in the left. The difference between these readings will give the diameter of that second ring. So we could get the diameter of the second ring, say mth ring, and we could get the diameter of m plus kth ring. K can be set as say 10. Then the difference between uh, second ring and 12th ring has to be noted, or the difference between uh, 10th ring and 20th ring, and so on. So we could get the difference between d square m plus k minus d square m, and the tabular column we could calculate this d square m plus k minus d square m. We could get the d square m plus k minus d square m for different sets of rings, and this the mean of this d square m plus k minus d square m has to be calculated. So this value is got, and then to calculate the radius of curvature is found out by using Boy's method. Maybe you already studied this in your school days. Actually, the Boy's method is like this. A given lens which is used in this Newton's ring arrangement is mounted on a suitable stand placed in front of an illuminated object, with the surface of the lens whose radius of curvature to be measured is away from the object. Then the position of the lens is adjusted in front of the illuminated wire gauze with a piece of black paper behind the lens, and till a clear image of the object is formed just by the just by the side of the object itself. This object means that wire goes. Let the distance between the lens from the object is measured, and let it be d, small d. Then focal length can be found out by using a plane mirror behind the lens, and the lens is then adjusted in front of an illuminated wire gauze till a clear image is formed, and then distance between the lens and wire gauze will give the focal length of the lens. By using this lens formula, 1 by f is equal to 1 by u plus 1 by v, and here in this case u is considered as minus r and v is considered as d. Minus r is taken because the negative sign is given for virtual object. Then 1 by f is equal to 1 by d plus 1 by minus r, or 1 by d minus 1 by r. That means the radius of curvature is, equation for radius of curvature is fd by f minus d. And by knowing this radius, or by calculating this radius of curvature by using this Boy's method, we can substitute it in the equation lambda is equal to d square m plus k minus d square m by 4kr. We could get the wavelength of light used in this Newton string arrangement. D square m plus k minus d square m is measured from the microscopic readings, and k can be taken as 10 or any value, that difference value, and r is the radius of curvature. We can use this method even to determine the refractive index of a liquid. For that, we have to introduce a drop of liquid in between this convex lens and the glass plate, and then we have to repeat the same experiment. Then the equation of the radius of the mth ring will be modified as rm square equal to rm square is equal to m r lambda by n, where n is the refractive index of the liquid. M r lambda, rm square can be written as m r lambda by n, where n is the refractive index of the liquid. So we can calculate.
So with air film, if dm and dm plus k are the diameters of nth and m plus kth ring, so with air film, if dm and dm plus k are the diameters of nth and m plus kth ring, d square m plus k minus d square m is equal to 4k r lambda. But whenever a thin film of liquid is placed between the lens and glass plate, we can measure this diameters as d dash m plus k square and d dash m, which is equal to 4k r lambda by n. So, refractive index of this liquid can be found out just by dividing these values, diameter values, difference in diameter values obtained without this liquid, and with the diameters of values obtained with the drop of liquid, whose refractive index has to be found out. So Newton's rings are actually alternate the bright and dark circular rings, and by measuring the diameters of these rings, we could effectively calculate the uh, wavelength of sodium light, and we can even calculate the refractive index of a liquid by introducing a drop of liquid between the lens and the glass plate. Thank you.